Welcome to the orientation session for BITS-ACM. Welcome to the orientation session of BITS-ACM. So allow us to introduce BITS-ACM now. We're a student-run chapter in BITS associated with the global body ACM. We're a group of about 80 nerds who share a common interest in computer science. Our goal is to not just promote computer science as a field of education, but also foster a sense of innovation and creativity among computer enthusiasts. We're not DVM and nor are we CC. Our goal isn't to work for fests. Okay, so now what do? We learn new tech ourselves and then we try to teach it to other Bitsians. We hold internal activities to ensure that our juniors learn to a point that they can teach others. We conduct software based events and expert talks during Apogee. We run several open source projects which are managed by our own seniors to allow the common Bitsian to work on different tech in a team. We create study groups so that juniors can study topics such as AI with seniors who are pros in that field. We conduct formal lectures to teach different CS skills to Bitsians. So now how can you get involved? There are multiple ways in which you can be part of what we do at BITS ACM. And you don't necessarily need to be a club member. You can join Silica, which is BITS Pilani CS community on Slack. BITS ACM is very active on Silica and you can engage with us there. We don't reserve any special learning material or events for the club members strictly. You can join us in our internal events if you're interested and enthusiastic enough, or you could be a part of the club and be at the forefront of all the stuff we do, interact with seniors regularly, and play a part of the events we plan and the tech we introduce in the campus. So how can you join though? We will talk about that at the end of this orientation. So this orientation isn't about ACM. It's about what you can do if you choose to learn tech in college. So we will cover a few fields like artificial intelligence, software development, which will consist of app dev, front end, back end, UI, UX and prototyping, competitive programming, blockchain, game development, systems programming, and theoretical CS. Feel free to ask questions and interact with other seniors after the orientation. The live stream is being monitored, so if you have any questions, you can drop it there. So now Shaz will start with artificial intelligence.
All right. So artificial intelligence. Next slide. So Larry Page, the co-founder of Google, he said artificial intelligence would be the ultimate version of Google, the ultimate search engine that would understand everything on the web. It would understand exactly what you wanted and it would give you the right thing. We're near doing that now. However, we can get incrementally closer to that, and that's basically what we work on. So this sets the tone of the infinite scope and possibilities that we have in artificial intelligence. Next slide. Yeah. But before that, what really is AI? We've AI is a massive buzzword, and there's a lot of terms. Artificial intelligence, machine learning, deep learning. These are the three major words that get thrown around. So, just to clarify what these words mean, artificial intelligence, the vaguest term of all of these, essentially means any form of intelligence demonstrated by a machine or something that isn't a human, and can range from the most complicated models to a very, very basic statistical algorithm, right? Then machine learning, that's a subsection of artificial intelligence. It's essentially the study and the implementation of algorithms such as statistical algorithms or any other form of algorithms that develop a sort of artificial intelligence in machines, or that develop intelligence in machines, right? Then a narrower term than this is deep learning. Deep learning is a specific subset of machine learning where we use specific neural networks, which are essentially networks that are modeled on the structures in the human mind that are called neural pathways. So these neural networks are used to create machine learning models that are intelligent, etc. And so deep learning is a subset of machine learning and is a narrower term than machine learning. So these are the three major terms that you will largely come across during in the field and even during this presentation. Next slide. So what's all the fuss really about? Where do we see artificial intelligence? Why is it so important, right? So just a few examples. For example, when you look at a For You playlist that Spotify makes, or a Discover section, or Instagram's Explore page, you're given a curated list of media that the app provides you for you to view, and these are made using recommender systems or recommended algorithms that use machine learning that works on your user data. And that recommends things for you to view, listen to, read, whatever, right? So that's where machine learning is used. When Google Photos recognizes your face or your friends' faces and creates albums, that's machine learning. That's specifically computer vision. When Siri and Alexa or any other voice assistant, listens to your voice, recognizes it, and understands your commands and executes them, that's called natural language understanding. That's a type of machine learning. When banks do credit scoring, they use different machine learning algorithms. When self-driving cars need algorithms, those are heavily complex and intricate machine learning algorithms that use various different types of machine learning to make sure a self-driving car can function. And these are all the examples, and these are very few examples. There's far more, and artificial intelligence is essentially part of every aspect of our lives essentially at this point, because we're such an online people right now. Next slide. Right. So in artificial intelligence or machine learning, what are the fields you will explore? One of the most common ones is computer vision. Computer vision is basically working with images and videos, and creating models that understand data from these images and videos, that can recognize things in the images and videos, that can generate images and videos. And there's a whole diverse field of what you can do within vision itself. Secondly, another very popular field is NLP, or natural language processing, which involves using text or audio languages, understanding them, and analyzing sentiment from those uh, from that text, creating chatbots or generating text, etc. All of these things come under natural language processing. And a third and slightly less common than these two fields is reinforcement learning. So while computer vision and natural language processing use supervised learning, which is essentially you have a training data which has an answer, and the model essentially trains on that data to get said answer. Reinforcement learning does not have a similar data set. It's more of an algorithm that's made to maximize or optimize some sort of reward. Say if you were teaching a program to play a game, and it finds itself in a position, and then based on that position, it executes a series of decisions to maximize a certain reward or an outcome. So that's what reinforcement learning is, right? What are the tools you'll use in the trade? First of all, the most common programming language used in this field is Python, right? Because Python is an easy to use language that's very easy to get into, and it's essentially the backbone of machine learning right now. But there's still diversifications happening, and people are moving into different languages like Julia, which is a new language that has come that has really grown in popularity, things like that. Then there's frameworks, like PyTorch and TensorFlow. So these are essentially uh, frameworks that are built that function on top of Python, that contain various libraries that essentially make it easier for you to implement the complex features that exist in machine learning in a very easy manner. So that's what PyTorch and TensorFlow, and there's other systems like Keras that allow you to do these things. So those are essentially the tools that you'll use if you decide to get into machine learning, and that's what you'll be learning at first. Next slide. So let's talk about the current state of the art in machine learning, right? I think a lot of people here might be familiar with what GPT-3 is. It's a state of the art. It's the state of the art for language modeling right now, and it's finding its applications in many use cases. It can be used for chatbots. It can be used for translation, like translating text from one language to another, but also it can translate code from one programming language to a different programming language. Things like various sorts of content generation, summarization, classification, things like that. Question answering, you can ask it questions and it would answer those questions to you based on the domain that you've asked the question in. And so this is the state of the art in natural language processing right now, and it's essentially used in various different applications in NLP. Next slide. In computer vision, NVIDIA is doing a lot of good things. These are two examples of really, cool new projects that NVIDIA has come up with. One of them is Gauguin. It's a software that NVIDIA creates which helps you generate photorealistic images. You can, as you can see on the GIF on the left, you can just create some very basic art using a few colors and your mouse, and it creates a real looking image that's like based on actual textures and landscapes, etc. And it looks like an actual real picture of a place that might even just exist uh, 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 through such little effort. And that's like the marvel of deep learning right now. And even though this is a very prototypical concept right now, but it can really grow very far and replace things like Photoshop in a few years. And you can try this out by yourself. If you just Google NVIDIA Gauguin, you can try this and you can play around with it, etc. Next, there's another thing that NVIDIA has come up with. It's called Ganimal, which is basically you can take a picture of any animal, say a dog over here, right? You can project the pose and the expression of that animal in the photo to a different animal of your choice. So say you could take this dog and then you could convert it to a dog of a different breed, say, or even some other animal, and it'll still have the same expression and the same pose. And like this image will be created entirely through machine learning models. And so these are two really cool examples of very cool things that are being done in machine learning right now, essentially. And now that's it for machine learning. I'd like to hand it over to the others to present software development.
Hello, hi, I'm Parth. I'll be talking to you guys about software development and what you can expect from the field, right? So, in a more arbitrary sense, what is software development, right? So, the short answer is anything you want it to be, right? But a longer sort of version is that it's a tool with which you can build literally anything, right? So if you think of any tasks that you do on any of your devices today, whether it's going through Instagram when you wake up in the morning, checking your email, checking WhatsApp, joining Google Meets, attending this session, Zomato, ordering food from Zomato, booking an Uber, all of this is powered by software development, right? And sort of the principle behind software development is that you build stuff for users, and like it gives you this confidence that you're able to like build solutions for anyone and everyone, right? There are pros to this, that you become really cocky because you think that you know that you can like build literally anything put in front of you. The cons are that if you have a friend who has a startup idea, they will come to you and ask you to build it for them. So what are the types of software development, right? So there's three main types of software development. The first would be front-end development. The second is back-end development, and the third is app development. And we'll be like going talking about these in detail. So let's start with the first one, which is front-end development, right? So what is front-end development all about, right? So front-end development of a software program or like a web app is basically the thing that the user interacts with, right? So for example, if you're opening up YouTube, what you see in front of your eyes, that is what the front end is, right? And the front end is basically what the user communicates with, how it like how the user processes data and how the user like engages with your service, right? And it's the design of this experience that you're creating for the user, and the programming, the functionality that you include, that makes like front end development so important, right? So what's some of the biggest goals for front end development, right? I think the most important one is to create a smooth or a frictionless user experience, right? So when we talk about front end development, the best pieces of front end development are the ones which have like the least friction, which it's easiest for the user to like work it through, right? So for example, bad software development is when you're stuck on ERP for like 12 hours and you still end up with a TTC. But an example of good software development is when it's like 4 a.m. and you realize that you've spent like the entire night scrolling through Instagram reels, right? So the idea behind like development in general is that it needs to be intuitive and easy to use, and front-end development like helps that because you're creating those experiences for people. Another important part of this is responsive design, right? For example, if I have a website but then I view it on my mobile and everything's broken, that's not good front-end development. So one of the important facets of front-end development is having responsive design. Next slide. Cool. So what are some of the important front-end frameworks and languages you can use, right? So the three pillars, I'd say, of front-end development are probably HTML, CSS, and JavaScript. HTML is basically like the building blocks for your front-end. CSS is how you make it look, and JavaScript is how you make it interact. Like how do you, like what functionality, what happens when a user interacts with it, right? So these are the building blocks for any like website, right? But recently, like in the past few years, we've seen the emergence of really like cool and new innovative frameworks which are based on JavaScript, which you might have heard of, which are React JS, which is arguably the most popular one. The next being Vue.js, and the third being AngularJS, right? These are some of the frameworks that are existing, but they are beneficial because for a large number of reasons. They make it very easy to like code, because for example, when you're using something like HTML, and for example, you have to like let's take the example of YouTube. If you want to show multiple videos, then in HTML you'll have to like repeat the code every single time. But through these JavaScript frameworks, you're able to like create components, or basically a block of code that you can then use out you can use everywhere, and that makes your code easier to use, less lengthy, more robust, and just it makes it an easier experience. Moreover, with JavaScript frameworks, what you're able to do is bring in external data, right? And we'll talk about this more when you get to backend development. But you've probably noticed that when we like look at user interfaces, the most important part is that you're getting data from somewhere. As you're watching this live stream, this data is being fed to your computer screen, right? And frameworks like JavaScript frameworks make it much easier to like interact with that data that's coming to you. And there's a large scope for like front-end development as well. So in case you're interested in front-end development, there are a lot of internships that you can get on campus through front-end development. You can apply for programs like Google Summer of Code, or also known as GSOC. And so that's the scope for front-end development if you decide to learn it. Moving on, app development. This one is pretty intuitive. Everyone has used apps on their phones. Next slide. Right. So what are the types of like mobile development, or what are the types of apps that you see, right? So there's two main types, right? The first one is native. And what native means is that it's like specific to your operating system. So I'm assuming that most people here either have an Android phone or they have an iOS phone, right? So what native apps do is they're built specifically for those for like Android apps, for Android phones, or like specifically for iOS phones. So you might be familiar with this, that like Android apps are written using languages like Java or Kotlin, and iOS apps are built using this language created by Apple called Swift. And that's how mobile development used to happen. So that's called native mobile development. But one of the biggest advancements that happened in mobile development over the last few years is cross-platform mobile development. It's a big word, but basically what it means is that you can take the same chunk of code and you can create it for multiple platforms at the same time, right? So, for example, if I'm creating, like, let's say the app for Google Pay, right? What Google did was they used a cross-platform tool called Flutter, and what they did was that they just had to write the app once, and it was usable both on iOS and Android phones. So that's the cross-platformness of it. So some of the two of the main things you'll see in cross-platform apps are Flutter, which is a language by Google which is gaining popularity, especially on campus as well. A lot of the app development that we do in BITS-ACM as well is also done using Flutter. And the second one is React Native, which, if you remember when I told you about React.js from 2 slides ago, it's basically a bridge off from that language used to make it for like different platforms. And the cool thing over here is that even though these cross-platform apps are not just for Android and iOS, but you can also use them on your computer and stuff. So that's where the cross-platformness comes into it. Next slide. Cool. So let's talk about backend development, right? So I spoke to you about data, right? About how data is probably like the single most important piece when you're communicating with something on the internet, right? Next slide. Right. So what is backend development, right? So backend development is basically the code that runs on the server. Okay. So question here: what is a server, right? So you probably like assume that this live stream isn't coming like it's not stored inside your phone, right? It's probably like happening on a computer in the middle of the ocean somewhere, and that's getting sent to your like phone, right? And that's essentially like a bare breakdown of like what a server is. It's a computer where like some other code is running. It does all of the hard work and then it sends it back, right? Why is this important? Because it makes websites dynamic, right? This would be a really boring live stream if it were just an image of my face, right? But the fact that like there's data coming to you as I talk live is what makes this so much more engaging, right? And the third thing is handling information, right? So again, like when we talk about data, often you have like apps that you need that like handle information, right? So when you're using WhatsApp web on your phone, when you're using WhatsApp web on your phone or your laptop, you're like, receiving messages instantly and you're sending messages instantly. And that's all powered through backend development. Next slide. Cool. So what are the main principles of backend development, right? The first is safety, right? So the backend contains critical logic without which your service can stop working, right? So it's way more secure to run. So it's way more secure to run it on a computer that you can like physically maintain and protect, right? So what does this look like, right? When you talk about authentication, right? For example, let's take Tinder, right? It would be really weird if like you could like have Tinder on your phone and like the authentication logic or the way that you log into the app is all done on your phone. So you can like log into like anyone's profile from your phone and then access that, right? That'd be a really weird way for Tinder to implement the service, right? But what they do is, and how every other service in the world does it, is they do it on their servers, right? Which means that there's a central repository from which you have to like send your like credentials and then they approve it. So safety is really important because there's like a way that like verification happens through one central unit, right? So that's why safety is really important. Cool. Next, performance, right? Performance is a very, very important thing, right? When you like make Google searches, you get like literally like millions of like results, right? And it would be like really disappointing if like you open like Uber on your phone and like 2 hours later text you, hey, we found a ride for you, right? That would be pretty annoying. So performance is a really important part of backend development, right? Because you have to like you have a lot of data, you have to filter it out to what the user is asking for, and you have to send it back within milliseconds, right? So that's why backend development is really important. That's also why a lot of like really high performance code is run on like servers outside servers that aren't like that in the middle of the ocean. Yeah, next slide. Accessibility, right? So this is another point, right? Your computer contains no code related to Google search, but it's a feature that you can use every day, anytime, from anywhere, right? So with good backend design, Google ensures that you can use its services from any device without downloading any software, right? You can run a Google search on your phone without actually having to have all of that data, like literally like billions of like results on your phone, and then your phone processes that. The fact that like Google has like a backend with which you can like, just send a post, like you can just send a request to, and it sends you the data back, is why it makes it so much more accessible. That's one of the most important pillars of backend development. Next slide. Cool. So frameworks. What are some of the frameworks you can use when you're doing backend development? The first is Django, which is written in Python. It used to be really popular in BITS because it's easy to learn, easy to use, and it's used by Instagram and YouTube. Django is based off of Python, and which is a very easy language to learn. And in case you also want to experiment with front-end development, you can also learn like this thing called Django templating language, which allows you to build dynamic front ends. So just search this up later. Another framework, which is a JavaScript framework, is called Node.js, which is written in JavaScript. It's very, very popular in general because and in bits. It's a little harder to learn initially than Django because you'll have to learn JavaScript first, but it is one of the most popular ones out there. The ones that, yeah, so it's used by Uber, Netflix, and PayPal. Cool. Then we have LAMP, written in PHP. No one uses PHP anymore. Don't use PHP. It's shit, outdated. Next. Go. So this is an interesting language. It's been picking up pace recently in bits. It's moderately difficult to pick up, so you should probably start with like something easier. But once you once you get your core fundamentals of backend development in place, Go is probably the best. Like you might find it the best experience. It has a rich standard library and has a high concurrency. So yeah. With that, I'll hand it over to Keshav to walk you through prototyping.
Yeah, so hi everyone, I'm Keshav. I'll walk you through the prototyping vertical of ACM. Next slide. So coming to what is prototyping and its tools. So I'll like explain you with this an example. For example, you have a really great idea and you spend like hundreds of engineering hours building something. And after building it, you realize that it's actually terrible. The application is actually terrible. The idea is not a product market fit, and whatever problems that have come up. So what do we do to avoid that? So before building that, it's usually prototyping. Prototyping is like you build a small sample before deciding on the final product. Software prototyping is about creating a model of the software first, incomplete versions of the software being developed, just to make sure that you are having a product market fit and like your application is actually worthy of your idea. So next slide, please. Yeah, the scope. While hiring new devs, prototyping, knowing design, knowing prototyping is always an added advantage. Like you must be thinking why is it important to the code and why everything, because when you see in a real much more realistic sense, a developer and designer, the communication can really be an issue. It can be a really cumbersome and irritating process. But for example, if you know prototyping, you know designing, then you can just pop into the design system yourself. You can pop into the designs, you can get the fonts, you can get the images, you can get things done really really fast and really really easy. Next slide, please. So yeah, as mentioned, the MVP is a version of a product. So prototyping is just making that MVP, making the basic layout and the basic structure. It does not exist for engineers or stakeholders. It's just for the product and the users of that product. Most importantly, is just the user design or the user centric approach that you use in a prototype or a UI UX space. So just to make sure that what you are building is actually for the user, not just for the company or for the developer who's actually developing it, because a user might have a very different opinion, might have a very different approach towards using the product, coming from the like rather than the engineer or the coder that develops it. There's also a direct correlation between the product success and the user experience. For example, if you've heard like all of you have heard and used Uber, right? But earlier also we had taxi services like Meru, which worked through an app, but they used to give us a call after 2-3 hours that your cab or taxi has been booked. But what Uber did, Uber created it a very user centric, a very easy mobile interface so that you can book a taxi in 4 to 5 taps. And now everyone's a witness to Uber's success, right? Next slide, please. So yeah, these are a few tips that one must keep in mind when getting started with prototyping. So like these are basically few tips and the steps that you do while prototyping something. For example, you're determining the goals that you're trying to achieve with your prototype. With the goals you're trying to achieve, for example, it can be increasing retention, it can be increasing click rate, It depends on the goals of the product or the prototype that you're building. Next is define the scope of your prototype. With the scope, you decide how much is it that you want to express in the prototype and how much is it you want to save in the development phase, because you cannot prototype everything, or you cannot prototype to the extent that the application is completely developed, because it's not really connected to the back end or the code or anything. It's just a show of slides. Next thing is planning your design. With planning your design, you think about the overall structure, layout, navigation, components, content, graphic, and like whatever that the user will interact on the screen. Next is building the prototype. Now prototype is a very iterative process, and giving it to the user, trying and testing and iterating it is very important when it comes to prototyping or designing. Then you collect and analyze that feedback, or according to the feedback, you change the design, you change the prototype, and as you change the design prototype, you give it to the engineer who builds it or the developer who actually builds it, and then you roll out the application. Next slide, please. Lastly, these are a few resources that you can check out for inspiration, for getting just what prototyping, what UI UX design, and what assets do you need. That's all from my side. Now I'll pass it on to Computer.
So, good afternoon. I'm Shivansh. I'll walk you through competitive programming. So, what is competitive programming? Competitive programming, as the name suggests, is to compete with the best of the minds around the globe. It can be classified as an intellectual sport where programmers use their problem-solving skills to solve challenging problems in a limited time frame. Next slide. So you may ask, why should we do competitive programming? Well, the primary reason for doing competitive programming is the sheer thrill. So you may ask, why should we do competitive programming? Well, the primary reason for doing competitive programming is the sheer thrill that it provides, the satisfaction you receive on getting that green tick or getting your code accepted. Another reason for doing competitive programming is for placements and internships. Next slide. Most of the big companies, including Google, Facebook, Microsoft, Apple, and Amazon, test your coding knowledge in their placements and internships. Due to this reason, good competitive programmers get much more opportunities than the ones who are not so good. Then there are some very prestigious competitive coding contests which have worldwide recognition, and getting a good rank in these contests can be really, really rewarding. We will discuss about some of these contests in the upcoming slides. Competitive programming also makes you a better programmer overall, as one is subjected to timed contests and is forced to write very efficient codes. It increases both your efficiency and the efficiency of code you write. As I mentioned earlier, there are some very prestigious competitive coding contests having worldwide recognition. ACM ICPC is the most prestigious competitive coding contest in the entire world. Getting a good rank in this one can literally make companies providing instant job offers. Then there are three very famous competitive coding contests by Google: the Code Jam, the Kickstart, and the Hash Code. And then we have another very famous contest by Facebook known as the Facebook Hacker Cup. To prepare for these, next slide. Next slide. Oh, yeah. To prepare for these contests, competitive programmers need platforms where they can practice and compete. Codeforces is the most used platform by competitive coders. It has roughly 2 contests in a week, with more than 25,000 people participating in them around the world. CodeChef and AdCoder are other popular sites for competing in contests. LeetCode, HackerRank, Spots, and ProjectEuler.net are mainly used for practicing problems for these contests. Although LeetCode focuses more on interviews and Project Euler focuses more on mathematical problems in competitive programming. So in which language should you code? For competitive programming, C++ is preferred due to its high efficiency and libraries, specially added for competitive programming. If you have no prior knowledge, then in my opinion, you should start with C++. Although C++ is preferred, you can use any language of your choice. Next slide. What we do. We create a community where we bring together people who are really interested in competitive programming. It helps in mutual growth and teamwork. Apart from participating in contests, we also conduct contests. You can see the poster of the International Coding League, which was conducted by ACM last year on CodeChef. We also conducted a freshers contest for beginners and are planning to do more of these this year as well. That's all for the competitive team. The next is blockchain, which will be presented to you by Varun.
So hello, this is Varun, and you must have all heard about the buzzword blockchain. So let's get to know why it's such a buzzword first, and then we'll get to know what it is. Blockchain is a simple ledger, simple technology which make sure that there is no trusted central organization. That is, there's no one at the center controlling every single thing and monitoring every single person. Let's say a bank. It has all your data. It knows how much you own. It knows how much you owe. It knows how much you are supposed to try give to someone else. It knows how much you are given to someone else, and that is what a blockchain tries to abolish. It is completely anonymous, such that a sender's ID is never given to anyone else. uh, it cannot be changed, like unlike a bank where they can simply change your records or something. Blockchain cannot be changed no matter what. It can be used to create real world assets, as we have seen. For example, Bitcoin is worth millions. We are not even close to that. So a blockchain can create real world value. It can be used to make smart contracts. Oh, okay, what's that? Smart contracts, is that some kind of contract? Not exactly. A smart contract is simply code running on the blockchain. It's almost like giving your entire bank account to a computer. And as developers, of course, we decide what the computer does. We can make it store values, run calculations, transfer money from this account to that account. But who stores these codes? Well, everyone. And who runs the calculations? Well, someone. We're not really sure about that. And someone will run the calculations for you. So what is the blockchain now? Simply put, okay, this is not simple. Distributed immutable ledger, that's not simple. So let's get to exploring what that is. Distributed, that expresses that it's distributed among every single computer. Immutable, which means it's unchangeable. Even if you change your entire blockchain on a single computer, you cannot change the blockchain on every other computer, and that will cause your computer to error out and not other computers. Ledger. A ledger is a history of transactions. So that is what these blocks are. Every single block is a transaction. Every single block is a function performed on the Ethereum network or any network that you put this on. What can you do after learning this block, and what can you do after learning technology? You can become a blockchain developer. That's just writing smart contracts, working for companies, and we'll see what these smart contracts can do. We have just told that they exist and they're computers, but what can they do? What are their possibilities? And then you can research ways to integrate with other fields, because right now blockchain exists as just blockchain. There's not much integrations. You can try to integrate it with IoT or even finance for that matter. And the security of blockchains, the anonymity of blockchains is trying to be broken because large corporations simply can't accept that they don't get data. So there are researches going on how to improve the security of blockchains. So when it comes to DAOs, this is distributed autonomous organizations, a huge name. We can just call it DAOs. These are just organizations that run themselves. We don't need to play with them. We don't need to tell them what to do and everything. They are ownerless. They are completely democratic. Democracy is the main point of the blockchain. These are just interconnected smart contracts, not a single smart contract, but interconnected ones. And they completely automate the process of this organization. And that is the point of this. So such an organization will not have errors. So it can expand and grow on its own up to how much ever we want it to. Right now, there was a recent report that said that top 20 DAOs are holding almost $6 billion in assets. Aave is a popular DeFi DAO. That is, it is a currency exchange, cryptocurrency exchange, and Maker is a similar DAO. So we'll look at a DAO example in detail. So assuming there are three people, art collectors, let's say, with money to spare 2 million, 3 million, and 7 million, and there is an auction. So when a DAO enters, what it does is it takes up all their money and gives them tokens. A token is nothing but a currency. It's just like a currency that's created by the DAO, and that's exclusive only for these three people. A dollar is for everyone. These currencies, this token is exclusive for this DAO and can be used only here. So when the auction comes up, let's say the Starry Night and Mona Lisa are on sale. The DAO will ask the group, of course. The DAO cannot take a decision on which art is better. And when it asks the group, they put out their votes. Of course, the person who has put up more money will have more voting power. And thus, Mona Lisa has 9 voting votes and the Starry Night has 3. So the DAO goes up and purchases Mona Lisa. And now the DAO owns Mona Lisa. Not these 3 people, the DAO owns Mona Lisa. And whenever anyone needs to sell the Mona Lisa, the DAO has to sell it, and the profit will be split according to the ratio. It will not be split equally. So this is actually a real DAO. It's called the Pleaser DAO. It recently purchased a music collection for $4 million. It's a Chinese music collection against rebels or something, but it was purchased by a DAO. It wasn't purchased by any person. So the possibilities with the DAO are infinite. You can literally run an entire company with a DAO. And since it has voters, it becomes a democratic company. We will not need CEOs. We will not need board members and stuff. So everyone will have power. Everyone will have a stake in the company. Everyone will have a say in the company. So next, NFTs. Like you could right now in the metaverse, there are people telling that I own lands in the metaverse. I own shops in metaverse. Let's not ask why. Let's ask how. What does a metaverse land mean? Why do people pay for it? Because they know that can't be taken. It's permanent. Because these are what are called non-fungible tokens. So what is non-fungible? It's a token which cannot be exchanged with another token of the same value. Suppose a 10 rupee currency can be changed with another 10 rupee currency and doesn't lose its value. But a non-fungible token cannot be exchanged, and that's why it's represented with artwork, because each artwork is unique. So why are they hype? So let's say many people have been. This is a simple example to show why NFTs are hype. NFTs are owning like the original. The Van Gogh painting, or the original cost, of course, millions of dollars. To be precise, it's estimated around 111 million. So why is that expensive when you can just take a JPEG and put it on your slides and print it out? Because it's the original. That's the thing with NFT, and that's why it's so expensive. But in some cases, NFTs are used as like an identifier that you're a member of a society or a DAO. Since DAOs give out tokens, sometimes they also give out NFTs such that it doesn't confuse between uh, two people. In the metaverse, every land, every game asset, every asset that you buy in the virtual reality is NFT, because each one of them is unique to you. Each one of them is registered to you and remain with you permanently, even if the game is dead. Supposing Ubisoft, like there was CS:GO, and it had skin exchanges and stuff. But all of this was controlled by CS:GO servers and stuff. And if the CS:GO servers goes down, you will never have access to any of these skins. But in blockchain, that is not the case. Even if any server goes down, it doesn't matter to you because you still own the game assets. So that is almost all I can say. All I have about blockchain and its related technologies. Over to Siddharth for game development.
Hello everyone, I'm Siddharth. I'm a member of ACM's game development team. I'm certain that you're familiar with what games are, even if you are not a dedicated gamer yourself. For definition's sake, a video game is an electronic interactive experience that involves manipulating an input device in some response to graphics on a screen. Can I go to the next slide? Okay, so game development is the art of creating games, and it describes the design, development, and the release of the game. It may involve generation, design, build, test, and release. While you create a game, it is important to think about stuff like game mechanics, rewards, player engagement, level design, etc. Can you go on? So there's a lot of like scope of development and your career growth in game development. You can work on like the tech giants such as like, as you've been aware, like Nintendo, Ubisoft, and Blizzard, Microsoft. Okay. Uh, so you can work as a game designer where you plan the design of the game, such as like story elements, how the levels are set up, how the story flows. You can work as a game programmer. You're supposed to like write code for how stuff interacts with each other and with your inputs. Level designer, like how each level tells its own story and like what puzzles to involve. Visual artists for creating 3D and 2D assets, audio artists for game music, and of course there's all have to be game testers. Can you go to the next slide? There's always also an option of working as an indie developer. Indie developers are small teams or like individual people who work on a tight budget and like small time constraint and produce like stunning games. Some recent like projects that have come up. The first tree is like an inspiration to everyone. It was produced by a single person over a span of 18 months and it generated like over $150,000 in revenue. There's Hollow Knight, which was developed by a team of 3 members. And like Among Us, like everyone knows Among Us, it was also developed by a very small team, and we have seen its success. Can you go to the next slide? Okay, so the software we use for game development, game for mostly you use a game making engine. So what that does, it provides you a simpler environment for writing and like visualizing your code. So for example, like we have Unity, and we have Unreal Engine, we have Game Maker Studio. Uh, Game Maker Studio and Unity are considered very user friendly. They can be used if you're beginning out. Unreal Engine is a bit more advanced. For creating 3D assets, you can use Blender, and for 2D assets, such as you'll need for some textures and backgrounds, you can use Photoshop or Maya. Can you go to the next slide? Okay, so these are some of our projects that we have produced at ACM. It was like an endless runner, coding running on like an FPS game. Next slide. Okay, so there are a lot more applications of working as a game developer other than like producing games. For example, one of the applications is virtual reality. You can create a simulated environment which can be explored. It has various applications such as like obviously in games. Other than that, you can create demos. Suppose like there's some architectural firm, it can uh, allow people to roam around in their new apartments without actually physically being there. Training individuals, for example, let's take an example of astronauts. You can like train them, not train them to work in like certain situations without actually like being in them. Tourism, like countries can create virtual demos of the places to increase the revenue from tourism. Can you move to the next slide? Next is augmented reality. So what virtual reality did was put you in a virtual world. Augmented reality is kind of the opposite. It brings the virtual world down to you in the real world. So as you've been like everyone would have been aware of the game Pokemon Go. You can like project models onto the real world and you can play around with that. It has like other applications as well. For example, let's say Google Lens. So you go through an image, it detects the outlines of it and it can like detect what it is. Can you go to next slide? The other fields are, for example, running simulations. So you can like model some molecules or some like a group of animals, and you can see how they interact with among themselves or the environment. These can be used for like various fields. For example, seeing how a molecule folds, like what structure it takes, or like how a certain species of bird reacts to a different change in environment. You can use cinematic rendering. As Unity like allows you to script around objects and like control the camera movements, so that can be used to create like stunning visual effects that can be used in like videos and movies. Reinforcement learning, you can build environments to train and test reinforcement learning models. For example, like you train a model to go through a game and like you can see like how it reacts to different changes in the environment. Can you go to the next slide? Okay, so Checkmate is game dev team's flagship event where we develop a game and host a contest around it with winners receiving prizes. This is the game we've been working on for the past few months. It's called Spectrum, and the key mechanics come down to complementary colors. You can change your color with power ups, and you have to navigate through a series of difficult puzzles and bosses. Anything that is your complementary color will kill you on touch, but like you can hit the enemies only if you are like their complementary color as well. Can you go next slide? Sorry, can you stay? Okay, so game development, like it has a lot of scope, and we have seen the peak, what people can do at the peak. For example, the modern games such as like the Horizon Forbidden West, the Forza Horizon 5, Demon Souls. We have seen like how stunning the graphics can become, and like even on the lower graphical side, it's more about mechanics, like how tight the controls feel, how well is your input translated to your player's movement. So there's obviously like scope of improvement, and it will definitely get better with time. So that's it from my side. You can contact me or any member of our team if you need any help, and we'll soon be providing you with some resources. Now on to the next section, system programming. Thank you.
Uh, Hi guys, nice to see you here. My name is Ayush. I'm going to be speaking about systems programming. And before moving on to any formal definitions or any jargon, I would like to start with a simple analogy. Suppose you go and you get your first salary and you buy a car. And so there's a lot of things you want to do with the car. You know, you want to drive it around, obviously, but you want to go fast. You want to drift it, maybe. You want to take your friends, take luggage. A car is basically made up of components such as an engine and wheels and steering wheel and transmission and such. Now, you as a driver want to do stuff with the car using these parts. How are you going to do so? Well, obviously, you're going to use the pedals that you're given, you're going to use your steering wheel, and you're going to use the gear shifter to do stuff. So now let me just extend this analogy to computers by saying that you have a system with a CPU, memory, storage, and you want to do stuff on your computer. But obviously, there needs to be some kind of interface, right? And this is where the concept of system software comes in. So if we could move on to the next slide. So systems programming, you can't talk about it obviously without talking about system software. So system software is a computer software which operates the computer hardware and provides a platform for people to run other application software on, right? So what is application software? That is computer software which helps the user in performing a specific task. And application software is sort of what you guys are familiar with when you say software, such as Google Chrome, Microsoft Word, Spotify, and such. So you need system software to basically run all of that on, because without system software, they cannot interact with your actual hardware. So what is systems programming? You're writing system software, which is software which closely interacts with hardware. It is resource constrained programming. You will find certain limitations in memory and all of that. And it is basically an infrastructure that you can develop other software on, right? So it acts as a middle layer between applications that you use and the hardware. So next slide, please. So what are the goals of system programming? Basically, what makes good system software? You need to have fast software because, if something is at the base, you obviously want it to be fast. And here we use things called parallel processing, which is you basically use everything all the CPU cores that you can, and you basically perform simultaneous stuff at once instead of doing it sequentially. And that basically provides you the ability to finish stuff faster. You need to have low overhead on your software because, as I said, if you have other software running on top, you yourself can't be a hog, right? You cannot really take up more RAM than required or more processing power than required. So you need to be computationally cheap. So now, thirdly, you need to be robust and fault tolerant. Now, robust means you are able to handle anything that is thrown at you gracefully, and you need to be fault tolerant. And just if anything goes wrong, you need to recover from it properly. And the reason this is important is, if something like Chrome crashes, well, Chrome crashed. But if something that Chrome and all the other things are running on, which is your OS, if that crashes, then your whole system is gone. And obviously, you can extend this to like really big computers doing really important things. If the underlying software there goes, then it's gone. And obviously, you need to have security. So you need to not let any bad guys in and give access to just what is needed. So, for example, if you download a game, you don't want them accessing your files, do you? So that falls on whoever is designing the system software to just say, okay, you can do this and not this. So that's security. And more, you need to be extensible. So how to explain extensibility? Say you have Google Chrome and we all use AdBlock, right? It's a great extension, blocks ads. Yeah. So why doesn't Chrome just put AdBlock into itself while shipping it? When you download, why do you have to separately add it on? And this comes down to extensibility, is that Chrome just wants to give you what you need to browse the web. And anything else, they said, okay, users will figure it out and make it for themselves, or someone else will make it for them. but they themselves want to be extensible. So Chrome allows users to add functionality to it without actually coming, shipped with that stuff. Next slide, please. So what are the languages used? Obviously, since we're programming at a low level, most popular is C and C++, which is, although it's older than my parents, it is still used very widely today. And the only problem with it is that it requires years and years of experience to write good C code, which is not buggy and not really crashing on edge cases. So recently, there have been newer languages such as Go. So Go is a language being developed by Google. It released, I think, in 2015, and it has C-like syntax, and it really provides easy concurrency. So as I mentioned before, parallel processing is very easy on Go. You won't scratch your head and pull your hair out while doing it. And it has an ever-evolving library of stuff. And another favorite is Rust. Rust is even newer than Go. It is very new. It has really safe code. And if any of you have programmed in C, maybe doing CP, you must have encountered segmentation faults, seg faults, which is what happens when you access memory which you're not supposed to. So Rust basically just completely eliminates seg fault by not even allowing you to run code, which will cause seg fault. And Rust is consistently ranked as a developer favorite in surveys by GitHub and other organizations. So next slide, please. So is system programming dying? Now you might be thinking, what is this old thing? Like, why am I going through all of this just to code in these old languages on such a low level when I have stuff like Python and JS, which, as Pars mentioned earlier, are pretty easy to use. So definitely not, because you need to keep in mind that a lot of applications need system software. So obviously there is an ever-evolving market for it. And moreover, the existing system software, like operating systems and such, they definitely need to, maintain themselves and need to be replaced with like certain versions and add new functionality. So people, of course, need it. And moreover, companies and people are constantly trying to develop more and more optimized and secure system software. So there is definitely a market for it. And although it seems kind of old fashioned and all of that, it's really not. So, the way I like to say it is that, you use cement and bricks to build your house for years and years. That doesn't mean it's really obsolete, is it? Even just because it's old. So, that's why. Next slide, please. Right. So I've told you, I've given you my word for it that, hey, this is quite not obsolete. So what can you actually make with it? Well, first of all, device drivers. So have you guys wondered how, you just plug in a mouse into your system and all of a sudden it knows, hey, this is a mouse. Or you plug in a keyboard and you press any letter and you say, wow, the letters are on the screen. So how does your PC actually know that this is a keyboard that I plugged in and if I press a certain key, it has to do this? Well, that is accomplished by a software called driver. So a driver is basically a piece of software which lets your computer know, hey, this is this device and this is the actions that it performs. So writing all that is the job of a system programmer. And this is not just limited to peripherals, also applies to your hard disks and all of that as well. Secondly, operating systems. Well, it's in the name. And OS is basically a software that manages computer resources, like your good old CPU, memory, and storage, and it allows programs to interact with them. So obviously, you guys have a good idea of what an OS is, and operating systems like Windows, Linux are used basically everywhere, right? Network libraries like BitTorrent and for people on campus, DC++. All these guys, if you've ever torrented, you know that stuff magically comes to your system and is just assembled. And so this is also the job of system programmers. Next video game engines, Unity and Unreal. As the video game dev team said, they use these software, but the software itself is developed by system programmers. So basically, we are allowing them to write their games, right? And moreover, codecs are basically softwares which take seemingly random strings of ones and zeros and convert them into videos, audios, and pictures. So like if you have an audio file, as you know that information in a computer stored in ones and zeros. So when you open that audio file, how does Spotify know that, hey, this is a song and I have to play this? So that is the job of a codec, right? And so yeah, they're pretty important, I think, in our day-to-day life. So next slide, please. So what is in it for you? Like, why should I bother learning this? Well, first of all, as you must have known by now, you will require and you will gain a really deep understanding of OS and computers. And basically, no matter what field you go into after that, you're basically going to be using a computer, right? And it really doesn't hurt to know as much as you can about the tool that you're using. So in that sense, it's really great. And you can exercise fine control over resources. So since you're programming at a relatively low level, you have direct control over stuff like the memory and what goes into the CPU and stuff. So it's always your choice when you're designing it. So that gives you a lot of like freedom and flexibility on how you want to implement or solve a certain problem. You can write efficient and lightweight code. So as mentioned earlier, low overhead, right? Computationally cheap. It runs on even the most low powered machines. So stuff like your Raspberry Pi and Arduino, which for people who don't know are really, really inexpensive computers. Like really tiny. They come in a box. You gain the ability to tinker around with your own machine and customize it to your needs. So this makes you a hacker, not in the sense of I commit cybercrime and fraud, but the hacker in the original sense is that someone who finds really ingenious solutions to problems that they face. And moreover, you write software which everyone else needs to run their applications on. So you can go to your friends and just tell them, hey, nice an application, but you wouldn't be here without what I did. So that gives you a nice power trip as well. So in that sense, these are what you gain once you learn system software. So now, obviously, can we move on to the next slide? Yeah, obviously, well, you need a job, right? So where can you work? Well, almost anywhere. So obviously, the big names of tech really require the best of system engineers. So you can work at Apple, where you could be the one coding the next version of iOS, right? Which is, I think, a pretty big deal. You could work at Google or Facebook, where, as you know, these companies have like humongous amounts of data, and they obviously need to store it, and they also need to keep everything running, because you can imagine what would happen if Google went down for a day. I think it did last year, and it was not a good time. So Google Cloud also exists, and there are so many servers that you need to write software for them. You can go work at Intel, where you can write the code which helps their new chip run, like without which their chip would just be just that, a chip. And you can go work at AWS, Amazon Web Services, where they too have millions of servers, which so many companies use their servers to keep their stuff up and running. You get to be the person who's writing code that enables multi-billion-dollar corporations to run their software on. And also you can work in NVIDIA. And as you know, that NVIDIA is also involved with, gaming, obviously, in graphics cards, but also ML and AI. And you can write software that speeds up these things and allows people to take full advantage of NVIDIA chips and all of that. So, well, you know what ML engineers do, you know what game developers do, but we system programmers, they really make their work possible by giving them stuff that they can run their software on. Like, for example, Unity, NumPy, and all. And it's really an interesting field. And as you can tell by now, it's just really essential for computing as a whole. So that's it from my side. And I will hand it off to the next functional programming and theoretical CS. Thank you.
Hello everybody, I'm Srijan. I'll be taking up theoretical CS. So theoretical computer science, next slide please. Yeah, theoretical computer science is basically all about puzzles. It is the mathematical foundation of all the computing you see. So think about the jigsaw puzzles you used to solve as a child, or some like mental ability puzzle you would have solved in the book and bragged about it to your friends. So this is what makes up the essence of theoretical CS. So in everyday computation, in every single code you write, there is a mathematical background to that code. The mathematics where that code came from, and that is what TCS deals with. So there are theoretical CS has been doing some ground breaking work, and it has been solving some very pressing problems, and like a lot of cutting edge research is still going on in TCS, and it will keep going on for many years. To give you an example, here you can see a small depiction of a very famous problem in theoretical computer science known as the traveling salesman problem. Now, the premise of the problem is very simple. Imagine that you have to travel a lot of cities, and you want to do it in a way that you only have to visit a city once, because it wouldn't make any sense that you have just been to a city, and to go to another city you have to go through that first city again. So that is just a waste of resources. You want that you can visit each city once, and then you want to end up back where you started, your home. So the premise of TCS, the premise of the traveling salesman problem of the TSP is really simple. It wants to find the path. It just wants to find the path in which you can visit each city exactly once and return to your starting position. Now, while this may sound very simple, it is so not. It has proven like very difficult to solve this, and there is still no generic algorithm that can do this for any model of graph. And it is very like, you may ask like, why is it really important? Like, okay, whatever, I can just go back to a city, not that much waste of time. But when you factor in like having to do it again and again and again, it just wastes too many resources. To give you an example in the industry, so you all see your computer chips. Computer chips have millions and billions of transistors and other little devices put into it. And to place these devices in the computer chips, you need to make holes in the chips. And these holes are made by a robot. Now, if there was a very efficient way to make these holes so that the robot can just follow a single continuous path, never go back on its path making those holes, it will save a tremendous amount of time, because you have to think there are billions of these holes. So solving the traveling salesman problem will save a lot of time, a lot of resources for a lot of people. And this is just one of the examples. There are many such things, such problems, such as P versus NP problem, which is one of the 7 millennial problems that if you solve, you receive a $1 million. So these are all which are being attempted to, which be solved through theoretical computer science. So next slide. Now, theoretical CS isn't just one thing. There isn't just one thing known as theoretical CS. It is actually the culmination of a lot of different fields having the same mathematical backbone. So, some of the most common fields of theoretical CS are algorithms and their design. So, this is what basically like out of all the fields I have listed, you will need to know algorithms in each one of them, because this is what you will be dealing with most of the time. So as I just mentioned, the traveling salesman problem, this is an algorithm, and similar algorithms to this you'll be implementing in theoretical CS all your time. Next, we have cryptography. So cryptography is just the encryption. So like if I have to send a WhatsApp message, so you see that in your WhatsApp message it says that it is end-to-end encrypted. So encryption like this preserve the safety of what you are doing. Like in banks, you do not want you want to have safe transactions. Nobody can steal the details of your transaction. Nobody can steal your money. So this is where TCS comes in. TCS is used to make these algorithms which keep everything safe. Even in mathematical finance, you can model financial markets using theoretical computer science. Then number theory and discrete mathematics, again, it is very widely used application of TCS. So I'll give you an example. Like think of Tinder. So how Tinder works, it basically works on a simple principle called as graph matching. So it takes a group of people and it tries to match them with their optimal partners. And the algorithm used to determine who the optimal partner is, how to determine this optimality, is done through these algorithms that we implement in TCS. Many other fields such as game theory and programming language theory, which is actually the study of the programming languages you use like Python and CPP. So you can see these are very all of these fields sound very different, but they do have the common bedrock, which is theoretical computer science. And this list also is by no means exhaustive. Like recently there has been a lot of advancement in computational biology even, and there have been integrations of theoretical computer science with art and design. So anything you put your mind to, you can find an implementation of it in TCS. Next slide, please. Okay, now of the quantum computing, a lot of you must have heard it is a lot of hype of quantum computing, and it is also an integral part of TCS. So what quantum computing is like? So all of you must be watching this orientation on your mobiles or your laptops. Now, your mobiles and your laptops are what we call classical computers. Classical computers work using bits. The fundamental unit of your computers is a bit, which can either be 0 or 1. It can be on or off, up or down. However, a qubit is very different to this. So a qubit can have the 0 and 1 state simultaneously. So I'm sure all of you must know of the Schrodinger's cat, how it can be both dead and alive at the same time. And qubit follows the same principle. So using this, a qubit can actually take up infinite values. There is no 0 or 1. You can have anything in between, and this gives qubit a very large representation power. So, like, to give you a very vague example, imagine like I have to go from Delhi to London. Now, if I tell you that to reach London, you just keep going north till you reach the right latitude, and then turn east and reach and stop whenever you reach London. So this is very cumbersome. If I just give you like sort of all these just north and east. So instead, if I tell you go northeast, you'll be able to reach like quite quickly. So a classical computer is like this. It will give you information piece by piece, whereas in a quantum computer, a single qubit will be able to process the entire information. So that gives a much higher representation power to qubits. Another very interesting aspect of qubits is that they cannot be copied. So, for example, say I am sending you a message. Now, if a third party, if a third person is watching me send that message, they can intercept that transmission and they can copy that message onto their own computer. So, sensitive information can be copied, your computers can be hacked. In quantum computers, this is not possible. It is not possible for you to copy a qubit. If you try copying a qubit, the qubit gets destroyed. So that makes quantum computers very safe and very secure. So like another like a very interesting fact about quantum computers. So there is a encryption scheme known as the Rsa encryption. It is actually used in your bank accounts to make sure that your information stays safe. And the reason why it is so popular is that because it is virtually impossible to crack. Like if you try to crack the RSA algorithm in a supercomputer, it will take approximately 300 trillion years for that supercomputer to crack the algorithm. However, a sufficiently strong quantum computer is able to solve that, is able to crack the RSA algorithm within a mere 10 seconds. Now, obviously, a quantum computer of this scale does not exist currently, but there has been work going on. Like the scale of quantum computing has been increasing exponentially year by year. So we might see in a few years of time that a quantum computer is just taking down all the encryption schemes that we have currently made, and we have to come up with new encryption schemes. So it is a very interesting field. It is on the rise, and it is actually available for all of us to use from our homes. So while a quantum computer might not be accessible to, you might not be able to build a quantum computer in your own home, but you can make an account on IBM, and there is an IBM software known as Qiskit. You can use Qiskit to run simulations on a real quantum computer, which IBM has built. So, a very interesting field. Next slide, please. So, at the end of this, you may ask, like, what is the use of doing all this TCS? It sounds very theoretical in nature, very mathematical in nature. Where will this get me? So, good news for you, TCS is a very fast growing field, and there are endless options for you to explore even after your college life. So, some of the most popular ones are that you can take up a job like a 9 to 5 job in R&D companies such as Microsoft or Google, even the big name companies, even the little small companies. Every single company these days has requirement for somebody proficient in TCS to some extent. Another option is that you can become a researcher, so you can try to find the solutions like I mentioned, the traveling salesman problem or the P versus NP problem. So these are all unsolved problems at the moment, and there is a lot of research going on at some of the very best institutes in the country, such as IISc Bangalore and even worldwide, such as the Max Planck Institute or MIT or Harvard. All of these institutes have a large team of theoretical computer scientists working on tackling these problems. Another option you can explore is, like, after studying TCS, you can join the academia. Most of the biggest institutes have faculty in theoretical computer science, faculty for game theory, cryptography. So that's the beauty of TCS. It's so wide, it's so extensive that you can find like work in almost everything. So that's how I'd like to end it. It is a very exciting domain to explore, and you don't really need any prerequisites. As I said, the thesis is all about just solving problems. So that is what you need. You just need that eagerness to solve problems, to find simple solution, less time-consuming solutions. So it is truly a field for everybody. So thank you. Now, Abhinav will take up functional programming.
Hi, so I'm Abhinav and I'll be speaking about functional programming today. So, next slide, please. Yeah, so functional programming is basically a programming paradigm that involves writing programs via the use of functions. When we say function, we are referring to the mathematical concept of a function here. I'm sure like you all studied like a function. When you give a certain inputs to a function always returns the same output. So in normal programming languages, we get things done by giving the computer a sequence of tasks, and when it executes, and then the computer executes those tasks. A functional program is a description of the output and not the steps required to produce it. We don't tell the computer what to do, but rather we tell the computer what stuff is in the form of functions. So the benefit of restricting ourselves to functions is that this allows for zero side effects. So what this means is that a function does not do anything apart from returning some value as a result, and this allows for some really powerful optimizations. In imperative programming languages, you will see that functions may sometimes return different outputs. You'll all encounter this in your CP course, which I'm sure you have this sem. So next slide, please. So one huge advantage of functional languages is provably correct code. Proving that your code is correct means that you will always assure it behaves correctly. Formally verified code certifies that hardware and software will always behave correctly, something that no amount of testing can do. So let's say I have a simple program and I give it a few. I can test if the program is correct by giving it a few inputs and output, and then checking the outputs. But suppose if I have a really complex program, so now eventually the complexity of the program will be such that I have to give it an infinite number of inputs, and I'll need an infinite number of outputs to check if the program is completely bug free. So this is a case where function programming shines. Function programming allows for a mathematical way to verify code, ensuring that it will run in all situations. You're basically translating math to code, and mathematical functions can be easily proved, which removes the need for testing tons of different inputs and outputs. This saves a lot of resources and will allow a program to work seamlessly. Next slide, please. So what are the future prospects for function programming? Well, function programming is still kind of bleeding edge, at least for production. But one area where it dominates is finance. Function programming is often used by trading firms and hedge funds. For instance, there's a huge trading firm, Jane Street, which primarily uses OCaml, a functional language for development. Since function programming allows for provably correct code, it has a huge role in these companies, ensuring that their programs keep functioning and have no bugs. Unexpected behaviors in code may lead to millions of dollars being lost in a matter of minutes. Haskell, another functional language, is also used at some big name banks like Standard Chartered. Apart from that, functional programming languages also find their place in companies like Facebook and Microsoft. You'll also really like function programming if you prefer a mathematical approach to coding, as it is based on lambda calculus and has deep ties to set theory and category theory. Slide change, please. Yeah, so that was it for today's orientation. The recruitment test will start from 5 p.m. After you finish writing the test, we'll soon release the results. And those of you who are selected will be given further tasks as per your field of interest. We'll be sending a doc with meet links for each vertical where you can come and interact with us until the test begins. And please join Silica. I encourage all of you to ask your coding related doubts there. There's a lot of seniors who are really cool and they're pretty much willing to help. Yeah. So